joint work with Zach, Kincaid, and Tom Reps. So we are interested in automatically checking whether an assertion in, say, a C program is safe, or disprove the safety of an assertion by witnessing an unsafe path. Typically, we can use 3 suites of tools shown above. So in the world of static analysis, there's a line of work that generates very good over-approximate summaries of program paths, and this is actually competitive with model checkers, improving program safety. But these techniques cannot find bugs. In the world of testing, there are many highly effective tools, for instance, DART, Directed Automated Random Testing, that can find very challenging bugs, but typically these tools are not designed to prove safety. And finally, we have software model checkers, and these can do both safety proofs and find bugs, but they can be slow and they can diverge arbitrarily. So the motivating question of our work is thus this: can we design a software model checking method that synergizes the best of both worlds, both powerful safety-proof machineries of a summary-generating static analysis and the bug-finding features of directed testing, with the result being an algorithm that is performant in both bug-finding and safety proofs. And this leads us to our new algorithm called GPS, which stands for Guided by Path Summaries, which uses summaries from static analysis to guide testing and invariant computation. So in what follows, I will show you some pictures illustrating the high-level intuition of GPS and discuss our evaluation results. Due to the time constraints of this presentation, I cannot cover everything in detail, so please consider giving our paper a read. So let me first explain the preliminaries through an example. As a starting point, we're given the program on the left. We translate this program into a control flow graph shown on the right, where the edges are labeled with transition formulas, which are Boolean formulas over program variables, and their primed copies denoting the next state. For instance, here the while loop on line 3 is translated into a cycle at B, and the assertion at line 6 is negated and translated into an entry edge into the distinguished error vertex at D. In addition to this, we also assume a summary oracle that can summarize the path condition of all paths from any given point in the program to the distinguished error location in terms of a transition formula. We'll later show you how we use this oracle and how we implement this oracle. And finally, the problem we're interested in is essentially finding a feasible path from, for instance, A to D in this example, which corresponds to witnessing an error path, or proving that no such A to D path exists feasibly, in which case we have proven safety. So now let me present some intuition about the approach. At a high level, we may think about the search space of our problem as the space of all program paths, shown in blue in the middle. And we wish to find a feasible path from S to T in the search space, which corresponds to witnessing an error path. So in the situation that we have found such a red path, which is shown in red, which essentially means we can declare the program as unsafe. But if we can somehow prove that no such red path exists from S to T, we can say that the program is safe. Now let us consider this situation, which describes a generic intermediate step in our algorithm. Here we have enumerated portions of the program space by executing tests that start from the entry vertex. But all tests we have explored thus far have not led to the destination vertex yet, so we haven't found a bug yet. In this situation, these tests stop in the middle at some arbitrary vertex between S and T. We would like to extend the space of search paths. To do so, let us pick some arbitrary vertex that sits between the search space on the left and the unsearched space on the right. This is where a previous path have stopped. Recall that we have this summary oracle called sigma, and let us pick a vertex in the middle, let's say V, and sigma of V gives a transition formula summarizing all paths from V to T, shown as the orange dotted lines on the right. So we ask sigma and see if we can query for a test consistent with the summary from V to T. More concretely, we take the path weight of the path pi on top, on the left, which denotes the path condition of arriving at V from S, and we compose it with the guard, which is just called the pre-operator here, of the over-approximate summary from V to T. And then we check if this formula is satisfiable via a SMT solver. Note that the pre-operator here stands for essentially it gives you all the pre-state, it quantifies out all the post-state variables and leaves all the pre-state variables in. So it gives you a generic pre-state with respect to this transition formula representing the summary from V to T. So if this query is satisfiable, we can actually use the model extracted from the SMT solver as a test, and we can extend the space of search paths a bit more further to say this particular vertex U. And in which case we might stop before actually reaching T because the summary oracle we use is over approximate. And hence not all tests we get from the guard of sigma of V can reach T. But at any rate, we have made progress by extending the space of search paths. In the other case, the formula we construct is unsat, and in this case, we use the unsat info as an ingredient to compute this state formula condition that witnesses the fact that T is unreachable from V. And in particular, this formula, which we name L of V, over approximates all states reachable from S to V and separates them from a state that can reach T. So intuitively, these formulas are actually invariant candidates, and indeed our full algorithm tries to use these state formulas to construct an inductive invariant. And in fact, we use Craig interpolation to compute such blocking conditions, and for more details about that, please refer to our paper. So to summarize, both SAT and unsat situations I mentioned before lead to a form of progress. In the case our query is SAT, we use a model extracted from the SMT solver to construct a new test, thereby making progress towards a counterexample. In the case our query is unsat, we use unsat info to compute blocking conditions, thus making progress to a safety proof. And we can iterate this process many times, and in eventuality, either we piece together a feasible path to error and terminate, or we block off all paths to destination vertex and declare the program as safe. This is the full intuition behind our algorithm. Now let me tell you how we implement the summary oracle. So in principle, any formula that soundly over approximates all paths between a vertex U and its destination vertex can work to implement sigma of U. Thus, we can use a wide range of tools that range from static analysis to invariant generation to implement sigma. But in our approach, we use a state-of-the-art summarizer called compositional recurrence analysis, which computes summaries for each loop in an inside-out manner, from the innermost loop to the outermost loop. And we compose the loop summaries together to form the final path summary. For more info, again, please refer to our paper. There are some additional contributions we describe in the paper, which I won't mention in detail due to time constraints. So these include a pre-processing technique to speed up summary computation asymptotically, and an instrumentation technique that guarantees the refutation completeness of our approach, essentially by making sure that the test generator does not generate an unbounded test and get stuck executing it in a loop. We further show that in the evaluation that this refutation completeness instrumentation technique is beneficial to the performance of the algorithm. To evaluate GPS, we compiled 3 diverse suites of benchmarks containing 297 call-free C programs in total. Our first evaluation involves an ablation study. So as you may have observed from before, GPS has several different components, and we study their effectiveness by iteratively disabling each component. So we visualize this as a diagram. On the top right, we have the full algorithm GPS. By disabling all the invariant synthesis features, so i.e. we don't compute the blocking conditions anymore, we get a directed testing tool, which we call GPS Lite, which enumerates all the feasible paths in a program. And this is shown on the bottom right. By disabling this refutation completeness instrumentation step I mentioned before, we get a refutationally incomplete model checking algorithm called GPS No Gas, which is shown on the top left. And then by further removing informative summaries from GPS No Gas, GPS becomes a software model checker with a directed testing component, but without summary guidance. And finally, if we disabled even the testing features of GPS Lite on the right, we get simply compositional recurrence analysis, which is just a static analysis and cannot refute any errors. And then on the bottom left, we get this classical algorithm if we sort of adopt a different strategy from GPS no gas, no sum, called lazy abstraction with interpolance or impact, which is implemented inside CPA checker as a strategy. And this is a tool that, this is an algorithm that enumerates program path in DFS fashion and lazily construct interpolants of infeasible paths to error, but does not contain any summary or testing features. So now we show the increase in the number of programs each variant can handle in form of a fraction of some number over 297 benchmarks total. So notice that as we trend towards the full GPS algorithm from the bottom left to the top right, the number of benchmarks each tool can handle increases, and thus the overall algorithm performed the best. The second experiment involved comparing GPS with several state-of-the-art tools. So we compared against the portfolio model checker Variabs and CPA checker, and then Symbiotic, which is a symbolic execution tool. So all three tools are top scorers on the software verification competition. And as you can see, GPS actually performed the best out of all four in all suites. So now let me briefly mention some takeaways. So if you're a static analysis person, you should be pleased about GPS because you can plug in your summary generating static analysis into GPS, and then you immediately get a model checker capable of finding bugs. Furthermore, the more precise your analysis is, the more performant your model checker is. If you're a model checking person, I think a key takeaway from GPS is that while refinement and maybe interpolation-based refinement has been a central technique in our area, in getting model checkers to converge, the results from GPS show that it often helps greatly if we adding a little info from concrete execution as well as static analysis. This is the end of my presentation, but in a nutshell, our GPS algorithm uses summary guidance to do both testing and safety proof synthesis. And in comparison with prior work, this corresponds to using both sides of unsat and sat info from SMT solver queries, whereas the baselines we build upon typically use only one side of such info. And spiritually, we're similar to a line of partition refinement model checking algorithms called Synergy, Dash, Smash, and McVito. But GPS then differs from them in that it uses summaries to generate a test and execute this test exhaustively until we have explored all the paths corresponding to this test before picking another one. Thank you, and feel free to ask questions if you have any.
All right, thanks. We have time for a question.
Hi, thanks for the talk. The graph is really clear for the intuition. And my question is from constraint solving aspect. So first, you are using, if it returns stat, you are using the model to resolve the same thing, but incrementally. So do you use some incremental solving techniques in the solver, or you just redo the SMT solving?
Good question. Yeah, we redo the SMT solving every time.
Second is, it is possible that for a single SMT solving, you can return several models instead of just one?
Yeah,
Does it helpful, or you just have one model a time?
We just pick a particular model at a time.
Why is the reason? So is it going to be helpful to return?
So I think there's a design space there. And on one hand, you can think about symbolic execution, which corresponds to sort of deferring, picking a particular model all the way until we have to do so. Mm-hmm. And on the other hand, there is us, where we use concrete testing, so we pick a very specific concrete model at a time. And we do this because the static analysis summaries we use is precise enough. So we want to bias as much as possible towards finding a particular error path instead of doing symbolic execution.
Yeah. Thank you so much.
One more quick one.
Very nice talk. If I understand correctly, the key innovation is to use summary to prune some like infeasible path. So I guess my question is, so in the case of onset, how do you utilize the onset result? Are you just pruning that the exact one path, or you can learn something from the onset that pruning to prune a lot of paths?
So this is the other innovation which we discuss in the paper. We call this dead-end interpolation. I think the key algorithm like in software model checking is this lazy abstraction with interpolance algorithm by Macmillan in 2006, and it does interpolation one path at a time. So we pick a particular path from source to error at a time, and then if it's unsat, we compute interpolance for them. But for us, what we do is we can interpolate at any arbitrary point where you have a prefix and you have an infeasible suffix, which is really a regular set of paths we extract from the summaries. And then we directly interpolate that particular path. And it's really a SAT query. So either you get a model back, or you get an unsat core back, which you can use to compute interpolance. Yeah.
Okay, we have to end it here since we're right at time or over. So let's thank Ruijie one more time. And everyone enjoy the break.